Tragically, this is our very last lesson in trigonometry for high school pre-calc class. It's a very sad day for me. We'll all try to cope. Luckily, we get to finish up with some new identities that are really cool and fun to work with. So the power reducing identities, you have the sine squared of theta. I can reduce this power if I want to by converting this or using the identity 1 minus the cos of the double angle of theta over 2. So twice theta over 2. Cosine squared of theta can be reduced by using 1 plus the cos of the double angle of theta, double theta, divided by 2. And tangent squared theta has a power reducing formula 1 minus cos of 2 theta divided by 1 plus the cos of 2 theta, which is very, very convenient if you have twice theta. So if you know what the cosine of twice whatever theta is, very convenient. But we don't always know that. Luckily, we have double angle identities, which will give us the ability to work with the cosine of 2 theta, or the sine of 2 theta, or the tangent of 2 theta for that matter. Double angles have, interestingly enough, more choices, which is kind of nice. Sine of 2 theta can be rewritten as 2 sine theta cos theta. So if you have a problematic angle that you could write as 2 times some other angle that you know, then you can solve this even when you don't necessarily have a common sine function for the angle you're given, right? So cosine of 2 theta is equal to cos squared theta minus sine squared theta. It's also equal to 2 cos squared theta minus 1. It's also equal to 1 minus 2 sine squared theta. And I won't go into great detail, but you can kind of tell we're dealing with something sort of Pythagorean-y. And I can, if I'm looking for the cos of 2 theta, if I have any one of these, it would be easy to convert with the Pythagorean identity into any of the other forms. So those sort of make sense, even though there are a lot of choices, it sort of makes sense that you would have those choices. And then the tan of 2 theta can be rewritten as single angles of 2 tan theta over 1 minus tan squared theta. Okay, so let's just do these again. There's just like we've been doing for the last week or so. These are just pluggy chuggy problems, and the best way to understand them is just to get some examples, plug in the values, chug away. So we want to find all 3 of the double angle values given that the sine of single angle theta equals 3/4. So I know because the sine of theta equals 3/4 that I'm talking about a triangle where the opposite is 3 and the hypotenuse is 4. I can also tell that I'm going to, in order to find all of the double angles, I'm going to have to find a cosine for, or have some cosine value for theta, also a tangent value for theta. So I'm going to need to know what the adjacent is. Sadly, it's not a 3, 4, 5 Pythagorean triple because 5 would have to be the hypotenuse. That's okay. I can just say that 4 squared equals, let's call this x squared plus 3 squared. So x equals, or x squared, excuse me, equals 16 minus 9. And so x equals the square root of 16 take away 9 is 7. So this is going to be root 7. Okay, now I have values I can work with. So the sine of the double angle for, I don't know what theta is. I still don't know what theta is, but I can find the sine of twice theta just by using the formula that reduces to values for theta. So if this is theta, twice theta, whatever this is, I don't know what it is, but I can calculate the trig values for that angle using theta. So that would be 2 times, well, the sine of theta we already know is 3/4, times the cosine of theta, which is adjacent over hypotenuse, √7/4. Now I can do a little bit of reducing here, and so I end up with 3√7 over 2 times 4, 3√7 over 8. That's the sine of 2 theta. So the cosine then of 2 theta is equal to the cos squared of theta. We already know the cosine of theta is, well, I'm just going to write it out. The cos is √7/4, and we want to square that, minus, well, I can use any of these. So maybe I don't really want to use cos squared minus sine squared. Maybe I want to use 2 times cos squared minus 1, or 1 minus 2 sine squared. I don't think it matters, because since I'm squaring a radical, it might be nice to get rid of that radical. So I'm going to go ahead and stay with the first form I started with. So cos squared minus sine squared, and sine squared is 3/4 squared. And so this is 7/16 minus 9/16. 7 take away 9 is -2/16, so that's -1/8. And then the tangent of 2 theta is, I only have one choice, 2 times the tangent of theta. Tangent of theta is sine over cosine, so 3/√7 divided by 1 minus the tangent squared. So I've got 6/√7. I think I'm going to keep it in a denominator for right now. 1 minus 9/7. 6√7 over 7, take away 9, -2/7. 6√7 times 7/2. I can reduce this, making -3, and then I can actually reduce this, making that a √7. So I end up with -3√7. So this time let's solve an equation. We want to solve the cos of 2 theta minus cos theta equals 2. And we're solving this on the interval including 0 and including 2 pi. So let's look at our identities and decide which would be the best one to go with, because we know that the double angle for cos gives us a lot of choices. So if I am able to convert this somehow to a function involving just cosine, then I can factor, so subtract by 2, set it equal to 0, use the zero product property. So the cos of 2 theta is going to give me sines if I use this identity, and sines if I use this identity. I think I want to use this version, 2 cos squared theta minus 1. So I'm going to write 2 cos squared theta minus 1, that's this, minus the cos of theta equals 2. And I think from there I can just simplify it right down. So let's see, I've got 2 cos squared thetas minus, let's rewrite it this way. 2 cos squared theta minus cos theta minus 1 minus 2 is minus 3 equals 0. And so if I do a quick substitution where I let the cosine of theta equal a, then I have 2a squared minus a minus 3 equals 0. This is just a magic number, so negative 3 times 2 is negative 6. Two numbers that multiply to give me negative 6, but add to give me a negative 1 have to be negative 3 and a positive 2. And I want factors, not solutions, so when I divide out by 2, I can set up my factors as 2a minus 3 and a plus 1 equals 0. So let's copy this back over here. I have 2 times cos theta minus 3 and cos theta plus 1 equal 0. And now I'm just where I was a couple days ago. 2 cos theta equals, 2 cos theta minus 3 equals 0, and cos theta plus 1 equals 0. So on the left-hand side, we have cos theta equals 3/2. And we immediately should realize that that can't be true, because if I were to graph the cosine function, cosine is as high as 1 and as low as negative 1. So the cosine of theta is never going to be 1.5. It's never going to be 3/2. So this is an extraneous result. And then on the right-hand side, the cosine of theta equals negative 1. So where does the cosine of theta, negative 1 is certainly a fine choice, just where does it happen? On the unit circle, the only place you get negative 1 for the x value is at pi. So at theta equals pi. And if I were to plug pi in here, the cos of 2 pi is, the cos of 2 pi is positive 1 minus the cos of pi, which is 1, or excuse me, negative 1. 1 plus 1 equals 2, and so I know that that's actually a good result. All right, so let's solve a power-reducing equation, and then, very sadly, let's call trigonometry done. Sine squared theta plus cos 2 theta minus cos theta equals 0. So since we're doing this as a power reducing, we want to do a substitution for sine squared. So come back up here to the power reducing. Sine squared gives us 1 minus cos 2 theta divided by 2. So 1 minus cos 2 theta divided by 2. Plus, and I'm going to go ahead and do a whole common denominator thing, right? So I'm going to multiply 2 times cos 2 theta minus 2 times cos theta, and all of these then would have the same denominator of 2, but it equals 0, so we don't really care about that 2. So I have, combining terms, let's see, let me combine terms. Cos of 2 theta minus 2, that's just a cos theta, minus cos, hey, look at this. Okay, I'm sorry, I got jumbled up a bit. 2 cos of 2 theta minus a cos of 2 theta is just 1 cos 2 theta. Okay, that part's done. Minus 2 cos theta, or too many 2's in this problem, plus 1, we don't care about the 2, equals 0. So can I factor this? I cannot, because 2 theta and theta are not the same thing. But I can convert the cos of 2 theta to 2 cos squared theta minus 1. Minus 2 cos theta plus 1 equals 0. Minus 1 plus 1 is 0. So I have 2 cos squared theta minus 2 cos theta equals 0. Factor out a cos, or factor out 2 cos. 2 cos theta times cos theta minus 1 equals 0. Now I can use the zero product property. 2 cos theta equals 0 wherever cos theta equals 0, and cos theta equals 0 wherever there's no advancement on the x-axis. So that's at pi over 2 and 3 pi over 2. And for our other factor, we have cos theta minus 1 equals 0. So cos theta equals a positive 1. So when I look at my unit circle here, cos theta can only equal positive 1 at 0 or 2 pi. So at, let's say 2 pi rather than 0. They're the same kind of angle, but since we're not looking at an interval that defines where we want to describe this angle, 2 pi works. So let's put this all together into a pretty little answer and say, therefore, theta equals pi over 2 plus n pi, which covers both of these, because if you start at pi over 2 plus 1 pi takes you to 3 pi over 2, and the intervals that we're actually being asked to look at is everything. So another n pi, and that works in reverse order as well. And at 2, well, all intervals or all expressions of the angle that lays across 0 or lays across 2 pi. So that'd be 2n pi. And of course, I do have to state that n is an integer multiple of my given angles.